When I promise you a detailed look at a piece of music, I have something different in mind from what most of you would expect. We'll talk about pieces of music in terms of components that music is built of, and we will handle musical harmony in an unconventional way. The pieces we focus on are musical intervals, pitched musical events that can occur at the same moment in time. Pitch is sometimes called the vertical dimension of music. Have you ever questioned why musical harmony is made up of such a small number of only 12 pitches per octave? Do you like beatless intervals and chords of stunning clarity and consonance? Do we really use all possible chords in tonal music? Would it be interesting to apply supplemental chords to create exciting additional chord progressions, even live on stage? None of these examples can be reproduced on a keyboard with conventional static tuning. We will reflect on the design of a novel musical instrument that considers dissonance and maximizes consonance of musical chords. We'll learn about the idea of tonal space, where related groups of musical intervals reside. Real-time aspects of a musical instrument are crucial for effective maneuvering in tonal space in a live situation. All of that shall extend the horizon for artistic expression. In physical terms, an interval can be regarded as a ratio of two frequencies. In this sense, a musical interval is represented by a real number. A rational musical interval I is defined by a ratio of two integers, which we can interpret as indices of harmonics taken from the harmonic series. When H is the index of a given harmonic from the harmonic series, L can normalize the frequency of this harmonic to 1.0. While both H and L are integers, L determines a set of possible rational musical intervals on top of the Lth harmonic. With a few mathematical transformations, we create an expression that represents all rational musical intervals in p-parameter lineage notation, the basis for the idea of tonal space. Watch what we can make out of it. Did you notice the blue markers used to illustrate intonation intervals? Intonation is an immediate fine adjustment of pitch, individually applied to notes, live at performance time. For our model of tonal space, we define more precisely: intonation is the typically very small signed interval between a pitch generated by a key with a given key descriptor that rings exactly in line with 12-tone equal temperament, and a deviating pitch referenced by the same key descriptor. Both pitches belong to the same pitch class. In contrast to the static nature of a tuning, intonation can incorporate severe dynamics. The term pitch class was established in 1962 for the set of all musical pitches of the same name regardless of octave. Octave-spaced pitches of the same pitch class are perceived as having a similar quality. They share the same chroma. A spectral chord is composed of at least two stacked intervals with frequency ratios taken from the harmonic series in ascending order. Within a spectral chord, arbitrary harmonic indices may remain mute. The lineage of a spectral chord is the numerical index of the harmonic that the spectral chord is rooted on. A septimal minor chord with the frequency ratio shown is said to have a lineage of 6. Chords form the zodiac signs in tonal space. We are going to observe where various types of chords appear. A major chord is formed from a major third above the root, which splits an outer perfect fifth. We can select from at least 4 minor triads. Augmented chords offer even more flexibility. A variety of diminished chords fit seamlessly into tonal music. A new chord type. So far, we have visualized all of our chords on a single plane of tonal space, even if I presented examples in different keys. To enable a musician to modulate freely through 12 keys with equally tempered bass pitches, similar tonal structures have to be built up for every pitch class, and we recognize the third dimension of tonal space is the dimension of pitch class. Each plane carries its own pitch class identifier. For spectral chords, we define the balance B, a new classification number relevant for a process that we call hyperbolic stretching of chords. In addition, B is a key figure for predicting a spectral chord's dissonance. The expression for B illustrates how to calculate the balance of a spectral chord. Instead of computing B numerically, it has proven helpful to represent B in the double bar format as shown. Of course, there is a much greater variety of chords than we have shown so far using triad examples. Let's listen to some added note chords and extended spectral chords. To perform hyperbolic stretching of intervals and chords, we extend our proven expression for calculating intervals with a new variable. We add a dynamic offset xs, the stretch variable, to the lineage L, which is left unchanged while hyperbolic stretching is in progress. To maneuver conveniently in tonal space, we can easily isolate any parameter. The pattern of intervals in tonal space exhibits an interesting superstructure. Intervals with the same p parameter form a hyperbola. When xs is modified in the same way for all pitches of an initial spectral chord, that chord performs hyperbolic stretching. Hyperbolic stretching differs fundamentally from MIDI pitch bending because the pitch of the root remains constant, but the chord changes its type. Other spectral chords are hit precisely being passed. The process of precisely adjusting a real musical instrument's pitches to render the set of desired intervals is called tuning an instrument. As a second meaning, tuning also describes the mapping of scale intervals to the keys, pipes, strings, or other kind of levers or oscillators of an instrument. Traditionally, a tuning is static. Pitches assigned to black and white keys or to the open strings of a guitar usually must not change over performance time. Our model of tonal space supersedes the traditional notion of static tuning with dynamic pitch mapping, a process where the player continuously assigns pitches to successive physical keys, live on stage at performance time. To implement dynamic pitch mapping, we decouple the instrument's keys from its oscillators by an abstraction layer called an interval sequence. In this context, an interval sequence is an ordered list of ratios between two pitches, displayed here for selected intervals over the 16th harmonic. This is the prototypical instrument I used to produce all of the sound examples in this video. In general, the player's left hand plays two mute intonation control notes in the intonation control zone of the keyboard. The right hand plays the audible voiced notes. This combination enables the player to access a surprisingly large number of intervals and spectral chords from tonal space. How does the intonation control keyboard work? Let the player's part be rendering a sequence of some lineage 10-based minor chords in various keys. each of them footed on an equally tempered root note. We start at D minor and get on with C sharp minor. From there, we step up in 4 semitone steps. Before each chord, the player presses 2 mute keys on the intonation control keyboard as shown. The lowest pressed key determines the bass pitch class, where interval mapping starts with the 16th harmonic. So the pressed B-flat key determines the pitch class associated with the 16th harmonic. The highest pressed key, a D at the beginning of our example, determines the 12 TET convergence pitch class, which always rings perfectly aligned with 12-tone equal temperament. All intervals between voiced keys are defined by our fixed interval sequence. Generally speaking, the distance between bass pitch class and convergence pitch class determines the lineage of a chord rooted on the selected convergence pitch class. The distance of 4 semitone steps is typical for all spectral chords rooted on lineage 10. Changing the distance between the 2 fingers of the left hand addresses other lineages. Remember that the bass pitch class is set by the lowest key pressed, and the convergence pitch class is determined by the highest key pressed. Setting the convergence pitch class can be interpreted as selecting one of 12 planes in 3-dimensional tonal space. This is a video capture from the creation of a sequence of spectral chords that normally is unplayable. Timing is a bit poor due to limited CPU resources. At the top, we look at a digital audio workstation with 2 MIDI tracks, the input of voiced notes and intonation control notes for the dedicated intonation processor. The application's intonation monitor in the bottom window visualizes the dynamics of intonation for all pitch classes. Listen to the creation of some augmented spectral chords. This is my first attempt to create a musical score for the audio you just heard. The top staff contains audible notes played by the musician's right hand. The second staff shows the mute notes to be played with the left hand in the keyboard's intonation control zone. Staff number 3 illustrates the frequency ratios of each respective chord. The staff at the bottom shows each note's intonation for information. Which intervals could a real musician play live on stage? All intervals marked with green crosses can be reproduced using the methods described earlier. The green dots visualize the implementation of our standard interval sequence, shown here with the 16th harmonic actually intonating at 0 cents. Yellow crosses indicate harmonics that the player can select interactively. The 22nd harmonic can be interchanged with the 23rd harmonic, and the 26th harmonic can be interchanged with the 25th harmonic on the fly. Pink crosses indicate 2 higher harmonics of particular interest. They would generate supplemental pure fifth above the harmonics indexed 11 and 13, which are already implemented. Harmonics marked with red crosses are not implemented. Now let's reveal the secret of the graphic that we already encountered in the opener of the video. This is a polar projection of one plane of tonal space. Each yellow ball represents a pitch. The center is the location of the pitch, where lineage L is equal to 1 and parameter P equals 0, which is the origin of the former Cartesian coordinate system. The lineage axis extends from the center up to the north. A clockwise angle of 2 times pi represents 1 octave up. In polar projection, our well-known horizontal lineage lines would appear as circles. For one octave in interval I direction, the polar projection shown uses lineage lines tilted by one octave in L direction to generate the spirals. Properly selected intermediary spectral chords can fit so seamlessly into classical chord progressions that even listeners with musically trained ears sometimes wonder if there is anything different about this music. So listen carefully.